Okay, so please settle down. Let's get started. Okay, so before we start, just an important announcement on your midterm. Okay, so the date is confirmed. The timing is 1 hour earlier. So originally I asked for 10 a.m., but then the office came back to say that the hall is not available from 10 to 12. So they asked to schedule 1 hour earlier. So 9 to 11 we have, but the duration may be 1 or 1.5 hours. Okay, so I will confirm again. So of course, at worst case, by 10:30 we'll finish. It will definitely not be 2 hours. Okay, so we'll start at 9, so it either end at 10 or 10:30. Number of questions, I do not know because I haven't started yet. Okay, and format, definitely got MCQ. I'm trying my best to stick with MCQ, so I don't need to do any marking. Okay, but if I cannot think of so many MCQ, then no choice, I have to put some structured question. Okay, so this is the format. So what is important is the date and the time. So 6 October is the Saturday, just after your recess week. Okay, so when you come back that week, that Saturday, 9 a.m., at worst, by 10:30 we'll finish. So if you have another midterm that starts at 11 or after 11, should be no problem. Okay, unless you have another midterm that also starts around 9 to 10, okay, then there's a clash, okay, then you make sure you let me know, and then you will come for the midterm just after this. That means at 12 o'clock, we will start another midterm at Com 2. Okay, I'll book one of the tutorial rooms and you have your midterm there. Okay, so those who email me to say that you have a clash, I will reconfirm with you again based on this new timing. Okay, so those who do not tell me that there's a clash or anything, I will assume that everybody is coming. Okay, so just take note of the date and the time and the venue. The actual structure and the timing, I'll confirm again. Okay, so don't worry, I'll also send an announcement on IVLE so that those who are not here will know about this. Okay, so let's finish up the lecture 9 slides and then we can go to lecture 10 slides by today. Just a few more slides in this. So we will stop at the branch instruction here to understand how the address will be updated in your instruction. Okay, so in this case we have branch if equal 9 with 10, register 9 with register 0, and it's equal go to n. And the thing that we want to look at is how will we encode this instruction in the binary format. So BEQ we know from the opcode what is it, correct? The register we know. Now the important thing is this n. So this n is referring to this label here, correct? So this is a label in your code. A label is not a compile code, it's just a placeholder to tell the compiler that it is referring to a particular line in your memory. So this immediate value, how do I get this value? So what is important for us to remember is when we are executing one instruction, the processor is already pointing to the next instruction. Alright, so if I'm executing this instruction, okay, after this instruction is fetched from the memory and sent to my processor, I automatically, by default, I am already pointing to the next instruction. So this n will now be relative to this instruction over here. And this n is how many lines away? 1, 2, and 3. 3 lines away, correct? 3 lines of code away. That means it is a total of 3 multiplied by 4 bytes away, correct? Why each instruction is 4 bytes. So the offset that you give is actually immediate value of 3. Okay? You only specify 3, you don't specify as 12 because you give it in terms of the number of words or number of instructions. The processor will know how to translate this into number of words automatically. Okay, so what we give here is the total number of lines of code or number of words effectively offset after the instruction that is currently being executed. Okay, so this and this and this opcode RS and RT we know from the our instruction set. The only thing we need to figure out is this. And to figure out this, you need to know where is my current PC and what is the address of the label I'm going to jump to. In this example, we are now going to branch backwards, correct? Branch back in the address. Why? Because here I'm checking for equal, and then I say go back to this line here. So what would be the immediate value for the second BEQ instruction? So when after I fetch this instruction and I am executing this instruction, my program counter already come here, correct? My program counter already come to the next line. So from this line here, okay, to go back to loop is how many spaces? 1, 2, 3, 4, correct? From the next line to go back to that label called loop, I have 4 words or 4 lines to go back to. So that is why the immediate value that I need to put in is -4. When you are writing your code in C and you compile, all this is automatically calculated for you, correct? Because the labels are already added by the compiler and it will know exactly which is the address line. Only when you are writing your own assembly language code, then you need to take note of these numbers. So just now we saw branch. Another way of moving from one address location to another address location is using jump. Why we have jump? Because in branch it is relative to PC, correct? So since it's relative to PC, I can only go to an address that is close by. Okay, but what if I want to jump further away, go to an address further away? So that is where the jump come in. Okay, and we can jump to anywhere in memory. Okay, so we say anywhere because there is still a slight limitation, but the compiler knows how to handle that. Okay, we'll look at that in a while. Okay, now if I say I want to jump to anywhere in memory, my memory is how many bit? My memory bus here, each address here is 32 bit. Alright, each address is 32 bit. So if I say I want to jump to this address, okay, let's say this address is A000FFFF, then I must be able to say jump to this address, correct? Okay, but this address itself is how many bit? 32 bit, correct? And my each instruction that I have in my MIPS is also 32 bits, correct? Can I put a 32-bit address in a 32-bit instruction? Can I cannot? 32 into 32, can I cannot? How many say can? How many say cannot? Okay, maybe I can answer for midterm. Okay, the answer is what? Cannot. Why cannot? Because you still have your opcode, correct? Every instruction, there is still some opcode. You still need to tell the processor what to do. If you just put 32-bit inside there, then what is the processor going to do? Correct? So there must be some bit reserved for opcode, okay, to tell the processor what is this instruction, what am I asking you to do. Then the rest of it is the data or address or something. So even though I have a 32-bit register, I still cannot use the full 32 bits to store an address or data because I still must reserve some bits for other information. So what can I do? I already have 6 bits that I need to reserve for the opcode, so I only left with 26 bits. Okay, so that is the 26 bits of the address I can specify. Why we want to keep the opcode consistent? Because again, we want to simplify the processor architecture. Okay, if you just say the opcode is 2 bits for jump, then other kind of instruction is 6 bits, other kind of instruction is 8 bits, then the architecture becomes more complicated. Okay, so in terms of hardware design, we keep the opcode bits consistent, 6 bits, so we only have 26 bits left for the target address. Now how do I play around with these 26 bits? We know that I'm only going to go to word aligned addresses to fetch my data or fetch my instruction. Your data may be in unaligned word or byte access, but your memory, that is your data that is holding all your instructions, will always be word aligned, correct? Because every instruction is compiled to a 32-bit instruction. Correct? Whatever code that you write, every instruction is 32-bit. So you know that if I'm jumping from one instruction to another instruction, that instruction will always be word aligned. Make sense? Your data you may access in byte, which could be word or non-word. Okay, but your instruction will always be word. So in that case, I know that my last 2 bits will always be 0, correct? I know that my last 2 bits of the address that I'm going to jump to will always be 0 because the instruction has to be word aligned. So that means what? That means now magically from 26 bits, I actually have 28 bits. Correct? Because I know the last 2 bits will always be 0. So I have 28 bits, but I still need another 4 bits, correct? So where do I get the 4 bits from? I take the 4 bits from the PC plus 4. So my program counter is already having the address of my current instruction. Okay, so I keep the upper 4 bits constant, and then I take the remaining 26 bits, and then I pad the last 2 bits with 0. Okay? So what is the maximum jump range that I have? 256 megabyte. Why 256 megabyte? Okay, if I say that I want to keep my upper 4 bits constant, so imagine that right now my PC plus 4 is 0001. Okay, in hexadecimal. So the maximum that my range can be is from all zeros, okay, all the way to what? F, correct? Okay, so this is the maximum range that I can jump to by keeping the upper 4 bits constant, correct?
Wait, the left side is bits, the right side is hexadecimal.
Yeah, all hex. I'm talking about all hex.
Yeah, but you wrote 12.
What?
You wrote 12 hexadecimal rather than 4.
4. Wait down. 8. Okay, salah. This is 4. Okay. I wrote extra. So this one should be how many? This is 4, 16, 32, correct? So this one should be 1 and 1 here, correct? Okay, so if I were to key this in my calculator, so in terms of hexadecimal, so this is the maximum I can go if, let's say, all my lower 28 bits are changing and my upper 4 bit is constant, correct? So now I assume my upper 4 bit is all 1. So this maximum value translates to what? Okay, this translates to what? Divide by 256, correct? You divide by 1024, divide by 1024, you get megabyte range, correct? So that's where you get your 256 megabyte range. So that is why we say that the maximum boundary that you can go to is your 256 megabyte. Okay, so even though I say technically I can jump to anywhere, I'm limited to 256 megabyte range. And that actually works out to be fine in most cases. Very rarely will your program exceed 256 megabyte. Okay, but if there is a case, there is still a way to do it, okay, which is a JR instruction. A JR instruction is a pseudo instruction. Okay, a pseudo instruction. That means you jump to a value that the register holds. So one of your registers, okay, maybe S0, S1 or whatever, one of the register will hold the full 32-bit address. Okay, and then I use that as the address that I want to jump to. Okay, so that is a pseudo instruction, but in terms of pure MIPS instruction, when you use a jump, you can jump to anywhere within a 256 megabyte boundary. Okay, and that gives you more or less most cases that you need to cover. So effectively, if I look at a jump instruction, what do I see? I see the 6-bit opcode here, and I see the target address. So this target address comes from where? This target address is the 26 bits that I specify, but what must I do? The 26 bit that I specify, I still need to add the last 2 bits below. Okay, and then I take the current upper 4 bit of my program counter and copy over, and that gives me the final address that I'm going to jump to. Okay, so that is how your jump instruction is translated into your binary pattern. Okay, so let's look at this. So in this example, instead of branch, I'm going to use a jump. Okay, if you look at this example and the previous example, it is the same thing. When I reach the end here, I jump to the label called loop. So for jump instruction, what is the opcode? I look at my instruction set, I will get the opcode, and the target address is obtained as what? This is 0010. How do I get 0010? Because this is address 8, correct? Okay, 8 is 1000, the last 4 bits. Okay, but since I only take the 26 bits, I discard the last 2 bits. Okay, so that's why I get the 10 over here. The last 2 bits are discarded. Okay, why? Because I will automatically pad the last 2 bits by the processor. Okay, when the processor takes this target address, what will it do? It will do two things. I will take and pad last 2 zeros in front, and I will take the PC plus 4 current value and add in front here to give me the final address that I'm going to jump to. Okay, so when we encode the instruction, we need to do the reverse, correct? We need to remove the last 2 bits and then take the remaining 26 bits. Okay? Okay, so that is how you come up with your jump instruction. Okay, so don't worry, when you look at the tutorial questions, you will get a better understanding how to do it. Okay, so sometimes when you want to do a branch, okay, so rightfully when we say we have a branch, it's a PC relative, correct? So it's plus minus, okay, based on 2 to the power of 15 number of locations. Okay, and why does it work most of the time? Because most of the time, this branch is used when we write loops, alright? When you write a loop, that is when a branch is used quite frequently, so you do something and you branch. But in some cases, you may also branch to some location that is quite far off. So if let's assume that right now I have some branch if equal instruction somewhere here, and because my code is very long, that particular loop or something I'm doing is very, very long, that label that I want to jump to, L1, is maybe beyond the range. Okay, it's beyond the range that is relative to the PC within this limit. Then what will my compiler do? Okay, my compiler will then try to replace and add additional jump instructions. So what will it do? It will try to jump nearby and then add a unconditional jump. Okay, so when you compile the code, when you write in C and you compile, what it will try to do? It will maybe try to branch to somewhere in between here, and then from here it will do a jump instruction to the new label. So it will try to make some adjustment to the code. Okay, so in terms of compiler, that is smart enough to do it. So it will know that whether this label is within the range that I can specify in my immediate value. If the 16-bit immediate value is not enough, it's not enough for me to specify the offset of where I'm going to branch to, then it will branch somewhere nearby, and then from there I do a jump. So effectively it's like 2 jumps to get to the final location. So that is again part of what the compiler will do for us when we are doing our C to assembly. So let's do a quick recap of the different addressing mode that we saw. Okay, so the first type that we saw was your register addressing. In register addressing, you specify 3 registers, RS, RT, and RD. Okay, always remember that the order is reversed. So if I say add, okay, S0, S1, S2, then this is my destination register, correct? Then the other 2 is my S1 and S2. And register addressing basically means that all my data is within my register, correct? Then I specify the operation to be done, and the final result is also back to my register. In immediate addressing, I specify 2 registers, and I specify a 16-bit immediate value, okay, which is represented in your 2's complement format. And what do? I take RS, do whatever operation or whatever that I need to do with immediate value, and the answer go into RT. Okay, and again the order is reversed, correct? If I say add immediate S0, S1, and let's say 5, then what happens? So this is my RT here, correct? And this is my RS. So in your immediate, you don't see a RD. You take it as RS and RT only. So RT becomes the end register where the final result will be stored. And then we saw base addressing or offset base addressing for your memory access. So when you're doing a memory access such as load word or store word, you are effectively doing 2 operations, correct? What is the first operation? You are doing a implicit add of the register with the offset value. Okay, so this is transparent to you. So the first step that the processor will do is it will take the register value, add with your offset. Okay, and that is pointing to some memory location. Okay, and if I'm doing a load word, then this go to my register. Correct? If I'm doing a store word, then this one go to my memory. Correct? So the load word and store word is only the movement of whether it's from register to memory or memory to register. So this is called your base addressing or displacement addressing. For branch, we saw the PC relative addressing. So in PC relative addressing, what you are specifying here is the offset. Okay. Again, it is 16-bit 2's complement limit. And what you are doing is you are adding it to your PC, program counter. If you look at the previous slide, we are adding it to the register that is specified in the instruction. When you do a load word or store word, the base address is specified in the register in your instruction. But if I'm doing a branch, the base address is actually the current PC. Okay, but it's actually what PC. When I say PC, this PC is actually the PC plus 4 already, correct? Because you already consider that you have already fetched the current instruction and your PC already incremented. Okay, so after the PC has incremented, then you use that together with the offset, and that gives you the pointer to the memory location. Okay, and that is where you will either jump to or not. So in this case, this end result, where will it go to? It will not be accessing your data in the memory, correct? And this end result go to where? Eventually, it's supposed to go back to my PC, correct? Because if the branch is supposed to be taken, then my PC must be updated, correct? Which we will see when we look at the data part for the MIPS. If the branch is supposed to be taken, that means the end result of this whole operation is to update my PC, to point to the new address in memory. Okay, so in PC relative addressing, we are not accessing memory or updating memory. We are just seeing whether the PC needs to be updated. Okay, so we are formulating a new address and then deciding whether the PC needs to be updated with this new address. And the last one we saw was your jump instruction. In jump instruction, you are unconditional. That means there is no condition to check. When you say jump, you will definitely jump. Okay, and you specify the lower 26 bits of your address, you pad the last 2 bits with 0, and you take the upper 4 bits from your current PC. And then you get your final address to jump to. Okay, so that is the sort of summary for this lecture here, or this set of slides. So you have your R, I, and J, which are the 3 formats that we see. Okay, so these are some of the examples that we have gone through. You can look at it yourself. So in this example, we give you the equivalent of what is the MIPS code and what does it actually mean. So you can go through in detail to get some idea how it works. Okay, so let's go on to the next slide, next set of lecture material.
I think they want to play Kahoot already.
No, Kahoot we played yesterday. Okay, so in this lecture slides, lecture 10, we are going to look at the instruction set architecture to understand a bit more of the hardware level. Okay, the hardware, how the processor is designed. Okay, so MIPS is just one of the many different architectures out there in terms of processor design. Okay, there are many other architectures and there are many other assembly languages with different characteristics. Okay, why we do not favor programming in assembly language for our high level is because assembly language is targeted towards the processor. Okay, so if today I decide to work on the MIPS processor and I say that I'm going to develop my whole project in MIPS, then all my assembly language code is targeted at MIPS. Correct? And halfway through the project, I suddenly realize that MIPS is not good enough. I want to switch to ARM processor, then everything must change. Correct? If I use assembly language. Okay, which is very troublesome and it's very time consuming. Okay, so that is why we always code at a higher level. Okay, so that the compiler does this difficult thing for us. Okay, when you code at a higher level, you just make sure you have the correct compiler. So if I write in C and I say I want to compile for MIPS, then you have a C to MIPS compiler. If I say I want to compile for ARM, then I have a C to ARM compiler. Okay, so we let the compiler do this heavy stuff for us while we just focus on the high level application. But having said that, when you talk about any form of embedded design, there will always be code that is written in assembly. Okay, which is the very low level code that sort of considers part of your boot up code and your initial system configuration and so on. So there will always be a small amount of code still written in assembly language because you need to do some things before the C program starts to execute. Okay, and in some cases, writing code in assembly can make your code much more efficient than writing it at a higher level. Okay, so that is why we still have to learn some of this assembly language. Okay, so there are two main types of philosophies for instruction set architecture. One is called the CISC, the other is called the RISC. Okay, so the main difference is the C and R, which is either complex or reduced. Okay, so there are two different sort of battlegrounds here. So there are people out there who feel the CISC is better, and there are people out there who feel the RISC is better. But over the years, okay, if you look at the trend, who is winning? RISC is winning, okay? And one of the most popular processors, or RISC processors is what? Your ARM processor, correct? Which is what you see in almost all your handphones, correct? If you look at Samsung, Apple, every time they advertise, if you look in the details, they always say it's ARM something, ARM something. Alright, so ARM is one of the most successful architectures out there. MIPS is also equivalently successful, but it's not so popular in handphones, but in a lot of other embedded systems. Okay, so MIPS and ARM are both equally powerful, and the reason why RISC has become very popular is because of what? A very basic reason, which is power consumption. Okay, because over time they realized that RISC architecture helps you to reduce the overall power consumption compared to CISC. Okay, and that plays a significant role for embedded system, correct? Because you are talking about battery power. You want to maximize the device that is running on battery. So that fundamental reason has actually sort of helped RISC gain market share over CISC.
X86 is still complex.
It is not so, it is still on PCs, but not so much on embedded systems. Okay, so let's look at the concepts of ISA design. So we're going to look at data storage, memory addressing, instruction set, the format, and encoding instruction set. Some of this we covered earlier, so it's going to be quite okay. Okay, so first let's look at storage architecture definition. Okay, so in von Neumann architecture, we say that data and instructions are all stored in memory. Okay, and what is a storage architecture? It's basically an idea of how data should be stored, okay, and how instructions should be stored. Okay, so we do not need to go into so many details. We just understand some of the different design that people have implemented. Okay, so one is called stack architecture, the other is called accumulator, general purpose, and memory in the memory. So we look at this picture, we get a better idea. Okay, so if you look at these 4 different storage architecture, what do you see here? In the stack architecture, you all know what is stack, correct? You all have used stack before. Stack is nothing more than just a block of memory I can push and pop, correct? So in stack architecture, how do I write a code? So you imagine that you use a processor that is using a stack architecture. If I want to do an add operation, what must I do? I must push my variable onto the stack, and then I say add. And when I say add, it automatically knows that the data is coming from the stack. So one is from the most recent, the other one is the second most recent. Okay, and then it does the add operation, and then it takes the data and write it back to my stack. So that is one way of designing a processor architecture. Okay, another one that evolved, of course, if you look at stack, it's very troublesome, correct? Then every time I have to keep looking at the stack and taking data from the stack, pushing and popping from the stack. Then along the way, they say, okay, why don't we have accumulator? So accumulator, basically, if you look at it, what they have is they have a accumulator is nothing more than just your register. Okay, in this architecture, what they do, they load a value into an accumulator, and then I say add with B. So, for example, A is an accumulator, and then B comes from where? Okay, B can come from your memory. Okay, and then when I say store C, I take it and write it back to another accumulator. So I have a few accumulator where I can store data, do the operation, and write back data. So when I do an operation, for example, add, I only specify one operand. Why? Because the processor already is designed to say that one operand only must be specified, because the other operand must be already in another accumulator. Okay, so for example, in this case, the add B is actually B plus A, but I do not need to say B plus A, because the architecture is such that when I say add, it will take this accumulator, add with A implicitly, and give me the result. Okay, so that is a different way of programming. So you can see that the way the architecture is designed will also affect how you write the code. Okay, so what we are doing, how MIPS does it, how ARM does it, is very much using the register approach, where you have a bunch of registers. Okay, if you look at our MIPS, you have register 0 to 31 with different names. If you look at ARM, you have R0 to R13, R14, and so on. So it's the same concept, it's just that they use different naming convention, and they have different type of use cases. In ARM, for example, in ARM processor, you will take data. So this A and B is from where? All these are from memory. Okay, so our ARM and MIPS, how they work is they take the data from memory, move it to my register, and when I do my operation, the data is in my register. And then subsequently, I can take the data and store it back into my memory here. Okay, so that is the register architecture that we are currently using in your MIPS processor as well as ARM processor. The other type is the more complicated, which is memory to memory. That means I can directly write an instruction which specifies that my data is also in memory. I take the data from memory, do the operation, and also write it back to memory, all in the one instruction. All in one instruction. So you can see over here, I never use any register. Correct? I say that my data A is in memory, data B is in memory. I say what I need to do, and I also say that the result will go back to my memory. Correct? So that is your memory to memory architecture. So from this you can see that your RISC processor is the one that uses your register to register, and your CISC processor uses a mix of register to register and register to memory. Okay, so that's the main difference. In your RISC processor, all your operations are based on register and register, which is very fast. Whereas in CISC, you can have instructions that are register to memory, which means some instruction can be very slow, correct? Now, always remember your memory is the bottleneck in your system. Anything that you do within the registers is very fast, because they're all within the processor. Memory is considered an external subsystem. So I need to go out, wait for the memory to reply, give me the data, then only I can process it.
Even for SSD.
Yeah, it is. Whatever is the case, memory is still the slowest. Your processor can run much, much faster than your memory access. Okay, so now let's take a look at memory addressing mode. So this picture I've drawn for you yesterday as well, correct? Basically, your processor needs to communicate with your memory. And to communicate with your memory, you need two main buses. One is your address bus, and the other is your data bus. Okay, we say K-bit address bus and N-bit data bus. Why? Because they do not need to be the same. Okay, your K-bit is the number of bits down here. That means this is 0 all the way to 2 to the power of K minus 1. Okay, this N is what? This N is this. This is 0 to 2 to the power of 2 to the power N minus 1. Okay, the N is the width of your data. N is the width of your data. K is the width of your address bus. So the width of the address bus basically tells me how many different address locations there are. Okay, N tells me what is the size of the data that I can store in each address location. Okay, so if I say that N is 16-bit means I can only store maximum of 16-bit data here. Okay, if I say my N is 32-bit, then in each memory location I can store 32-bit data. Okay, so that is your general architecture. Your processor has a few registers. So there is an address register to keep track of where is the address I'm pointing to. Then there is also a data register, correct, to keep track of the data that I want to write to memory or read from memory. So these are all internal to the processor. Okay, now another important thing called Endianness. Okay, when I was a student and my professor said Endianness, I thought he was bloody hell trying to be racist or what. Okay, but no, Endianness is a correct term. Okay, so what is Endianness? So there's big Indian and little Indian. Again, we're not trying to be funny here. Okay, I remember after this when I had the Kahoot quiz, everybody say biggest Indian, smallest Indian. Okay, so what is big Indian and little Indian? Anyway, since I'm an Indian, I can make this joke. It will not classify as racist. Okay, so big Indian and little Indian means what? It's just the order of a multi-byte data in your address space. Okay, so if I have a multi-byte data, okay, A, B, C, D here. Okay, 4 bytes of data. Essentially, this is a one word. How do I store the data? So if I look at my address, so this is address 0. Okay, so this is address. So in terms of address, I have address 0, 1, 2, 3. Okay, as we know, MIPS uses byte addressable allocation, correct? That means in each address, you store 1 byte of data. Each address is store 1 byte of data. Now, how will I store this forward data? So this forward is called dead beef. So again, I always question, why is it called dead beef? Why not dead cat or dead fish or something? Okay, why? Because you don't have a S or a T in hexadecimal, correct? In hexadecimal, you can only come up with dead beef. Because all of these letters can be represented as hexadecimal number, correct? Okay, so in dead beef, how will I allocate dead beef to my 4 different bytes in Little Endian or Big Endian. Okay, so in Big Endian, your most significant byte go to lowest address. So your most significant byte is what? Your DE. Alright? So my DE will go to my address 0, and then you carry on. Okay? In least significant byte, in Little Endian, your least significant byte go to your lower address. So your least significant byte is EF. So your EF go to address 0. Okay? And then you carry on from there. So it's just a convention of how data will be stored in a byte addressable memory. Okay, and this is very, very important because this can be a cause of a huge headache for you when you are having multiple systems trying to talk to each other. Okay, why? Because if you have one processor that wants to send data to another processor and they are both using different Endian format, okay, then you must be very careful how I transmit data around. Okay, if you are not careful, then you receive all the data, but you rearrange everything the other way around. Correct? That everything looks funny.
The useful method is that the information is big endian, whereas the Intel processors are usually little endian.
Okay, so rightfully, okay, most Intel processors have switched to Little Endian. I mean, the Intel processors have always been using Little Endian. Okay, so this also plays a part in your MIPS tools that you use. Why? Because MIPS does not specify the Endian format. Okay, that means if I'm going to design architecture using MIPS, as a designer, I am free to choose what I want to use. Correct? So if I want to design a MIPS processor using Big Endian format, also is acceptable, or Little Endian format also is acceptable. Okay? Now, how does this play a part when you do your lab? Okay, in your lab, you're going to use the simulator tool. Correct? And your QT-SPIM simulator tool, what does it do? It actually follows the Endian format of your processor in your laptop. Okay? So if you are using Windows, most likely you will only see Little Endian format when you look at the memory. If you are using MacBook, depending on which version of MacBook you're using, because MacBook used to use Motorola processors for quite a while before they switched to Intel. Okay? So when Motorola was being used, they follow Big Endian format. Okay? When they switched to Intel, then they switched to Little Endian format. Okay? So when you use a MacBook and you're using the QT-SPIM, the order of your data in your memory may be different from your friends. Okay? Depending on which processor you're using. Okay, so this addressing mode we have seen before, register, immediate, and displacement. And in terms of the different addressing mode, we only need to look at the first three because these are the first three that we are using in your MIPS. You can see the rest of them. For example, I can do an add operation directly with a memory. Correct? I can do operations directly with memory. And all this is not allowed in your MIPS. Alright, your MIPS architecture does not support it. Okay, so you only need to understand the first three. Why we put the rest is because in future, if you work with a different processor that is maybe CISC architecture, okay, or supports all these different addressing modes, then you must understand that it is possible that I can write an assembly language instruction that can take and manipulate data in memory in the instruction itself without moving it to my register. Okay, so I think we will end here today. Just a few more slides, but never mind. We will end here. So next week, we will finish up and then we will carry on. So we're going to go more and more in-depth into the data part and the flow of instruction. Okay, right now we are almost done with understanding how MIPS assembly language translates to your binary bit pattern, correct? Now the next step is how these bits flow through the processor to allow your processor to make the decision, correct? If it's add, what should I do? If it's a load, what should I do? Alright, so that is the next few lectures, MIPS architecture. Okay, so thank you. I will see you all next week.
For the tutorial, actually, when I read the code, I don't really understand is that because so it works like the normal, it works down, right? So we just one line by one line, right? So if for this loop, right, so it only like if T0 is not equal to 0, then means that it will exit, so it will go to this loop, right?
If it's equal lah,
So
correct.
it means that this loop actually it covers the whole thing, right? Or but then how about this loop?
Yeah, so you don't consider this as because the loop, in a sense, you think of it as a loop, but you can also have if else. This is the if else.
Yeah.
This is the loop.
Yeah.
Alright. So this is to check whether the data inside T2 is 0. If it's 0, then you do this.
So if it's not right, it won't do this, right? So it will just start here.
No, if it's equal to 0, then I come here. Alright? If it's not equal to 0, I come here, then I still do this.
Oh, you still do
Yeah,
this.
I still do. Because you still do extra line by line.
Okay, so only if it also it will just go extra. So this is a nested loop, right?
Wait, it's not nested loop, this is if else.
Okay.
If you're checking if this condition is true or not true, then do something.
Yeah.
This is the loop.
But then this XOR doesn't belong to this D0, no, right?
It's
What?
part of that. That means, you see, this is like an if else because if this condition is true,
You will go to the
then
X.
I go to here.
Yeah.
But if it's not true, then I will do this. Right? It's just like in your code, you say if this condition is true, I do this.
Oh,
Right?
okay.
So it's just like that.
Okay, I get it. You mentioned that memory was the bottleneck. Really appropriate to say that the bus is actually the bottleneck instead of the memory.
No, not the bus. Because the bus is just sending the bit out. The bottleneck is the memory because the memory is very slow to respond.
Okay, so we can assume that let's say it's register system, right? Within the processor, we can assume that those registers respond faster than those in the memory.
Yeah, because the data in the registers is immediately available to you. You need to wait. Data in memory, you need to wait.
So purely off the fact that the RAM actually is outside of processor, we can assume that it's more.
Outside, it is more of the memory technology, I would say.
Okay.
Just now, you mentioned in the slides that the instructions and data are transferred by the bus from the memory to the processor. So the data is stored inside the registers, but what about the instructions?
Instructions also in the
Memory. So every time the processor needs to process instruction, you need to go by the last tick to transfer that.
So actually, every instruction actually got multiple cycles. Because first you need to fetch the instruction. Then the instruction, if you say it is a memory access instruction, not word store word, then inside the instruction you're going to access memory one more time.
Oh, so it's like the instruction as memory instruction.
Correct. If your instruction you just add, then after the instruction come in, then I just do everything in the processor.
Sorry, I'm wondering that last week we talked about incrementing the pointer. So if the pointer is pointing to integer, then you increment by the size of the integer.
Correct.
So because I read that the size of integer is not fixed.
Correct.
Different machines. So it's just like whatever is the size, you increment by the size.
Yes. So it will increment based on the size of the machine that you're using.
Okay. Okay.
Yes.
You know about me about this.
Yeah, I think you told the office
I actually went to see the.
Diana, is it?
Sorry?
Is it Diana? You want to see Diana?
I always thought a lot about it, and I need to you need to see a doctor first before getting for the exam thing. Yeah, like by that's next week. So, but you say for midterm, you can arrange it for.
So the midterm, if you want to do the second half, then you can come at maybe 12 o'clock. Because the 9 o'clock one, I will end at either 10 or 10. If you need more time, then I can do it in the second sitting.
Okay, 12. I don't know. It's just like this lecture and the previous one, I feel kind of really lost. Is that normal?
It is quite normal actually. If you read. When you go through the tutorial, does it help?
I was having quite a bad few weeks these days. So it's like only going through some of the tutorials, just some of them, but not the latest one.
Okay. So what I suggest is you when you go through the tutorial, you try the question. If you still cannot figure out what's happening, then you come and see me in the office. And then I'll discuss with you.
Just then, if I want to do decently in midterms, what should I do? Maybe just study.
I think go through all the material and revise your tutorials and labs. That's the best. I mean labs as in, at least the concept is like, for example, because there is CPU involved,
Just sub one thing.
there is news programming involved,
Yes.
and then there is the news processor. Correct. So as long as the concepts are there, I think you understand. If you look at the how quiz, they give you some idea of some of the questions, the kind of MCQ questions that get
Oh yeah, that's true.
Jump.
so that gives you some idea like kind of questions.
Like negative.
So you let me know when you want to come and see me. Then you will meet up.
If I got troubles, I think I'll drop you an email. Okay.
That's right. The jump, just now you said we can only jump 256 only. Can we jump backward?
Yeah, you can jump to anywhere.
So it's backwards 256 and forward 256? Or is it 128 each?
It is relative to the current PC. That means, if let's say your PC, if your 256, okay, rightfully, from where you are, you can jump to anywhere, 256, correct? Okay, this 256 is assuming the 4-bit never changed. But if the address you want to go to, the upper 4-bit must change, then there will be other pseudo instruction that is generated.
Do we need to know that?
No need.
Oh, okay. That's the main part. That's the main part.
Because that one is, in the case, very rare case where it go beyond the boundary.
Because usually the loop will,
No,
the
whole
jump
program
will be
will
within.
never be 256 megabytes. 256 megabytes is very, very big. It's very, very big, yeah.
Maybe I write 200 million of
So,
so if I go backwards, it will change the first format.
if you specify that you have to jump backward, correct, then if you're writing the code yourself, correct, and then let's say the label is beyond the boundary, then the compiler will say it's error. Then you need to put in an intermediate jump, at least 2 jumps.
But the limit 256 is like from PC plus 4 all the way to the 256. Because once you executed it straight.
256 is considered the absolute boundary because assuming that you start from 0, that means your current address is let's say 0, and then maximum I can go is 256. But if you're starting halfway through, correct, then of course it's not 256, it's less than 256. Alright? But if you say you go backward, then when you go backward, your upper 4-bit might change. Alright? So that is where the thing come in, whether you need the compiler to put in another jump for you.
That's why you mentioned the challenge whereby you need another jump, but like you say, usually they won't go across 256 megabytes. So usually one jump should be sufficient.
Jump usually one jump is sufficient, but run sometimes is not sufficient.
It needs to exceed, right? The MIPS compiler will auto help us.
Yeah,
auto jump, right?
Correct. That is if you write in C.
Or in C, but the MIPS itself will.
No, that one you show as error, then you need to fix it. Yeah, I'll upload idea.
For this jump J for the first the address that we want to change, why do we take it from the PC?
Because you need 32 bits for the address, right? So since I can only specify 26 bit, and then I know the last 2 bit is 0, right? So then I got 28 bit, then I still need 4 bits from somewhere.
But what I just want to ask, why do you take the first 4 bits from this? Like what's the relevance
Because
of this?
the idea is that you will most likely not change the first 4 bit in the new address. So by default, they assume that the upper 4 bits of your PC will not change the new address, which will be true for most cases, lah. You know?
I mean, but if you assume that this, I'm just curious, like if you assume that these 4 bits will not change, right, that means you are already within the boundary. Right?
Correct.
So that means.
That means you are trying to say that you're going to be only within the 256 megabyte boundary.
Oh, okay.
Right? Which will hold true for 99% of the cases.
I think the start is you want to jump backwards, then the 2s complement, then the 1 would be.
No, that's why there's no 2s complement.
Oh,
This is not immediate value. This is the 26 bits of the address.
oh yeah. So if it's the
Is
I then
It's just 26 bits like this. Don't think of 2's complement in this.
so but the
The
I
immediate
J,
one, that one is 2's complement, yes.